Hello, my name is Heather Wilkins. I'm Manager of Business Development at ATA Engineering. I'm pleased to be here today to discuss our Phase 2 STTR project titled Systematic Fatigue Test Spectrum Editing Using Wavelet Transformations, which is NAVAIR topic 18B-T029. The principal investigator for this project is Mr. Tyler Van Fossen, who works in our office in Denver, Colorado. I'll give you a quick overview of ATA's capabilities, and then I'll dive into this project and describe some exciting developments ATA has made on accelerated fatigue testing. ATA provides innovative solutions through analysis and test-driven design by focusing on the engineering needs of manufacturers in addressing their cost, quality, and time-to-market challenges for mechanical and aerospace systems. ATA is an all-employee-owned small business, which really promotes an entrepreneurial, can-do attitude. We currently have nearly 200 employees, the majority of whom hold advanced degrees. We use testing and analysis coupled with computer-aided engineering and mechanical engineering software to solve problems in the aerospace, defense, themed entertainment, and industrial markets. We're experts in applying advanced mechanical engineering software to design, test, and analyze mechanical engineering structures, with particular expertise in complex, highly engineered structures subject to severe dynamic loads. Besides our headquarters in San Diego, where I'm located, we also have offices in Los Angeles, the San Francisco Bay Area, Denver, Albuquerque, Huntsville, and Washington, D.C., so we can provide local, full-service capabilities and personal support to our customers. As an example of one of our projects, here you see the Mars rover Curiosity, for which we provided analytic support for nearly 4 years ahead of its launch. ATA continued our legacy of supporting the exploration of the Red Planet by supporting NASA JPL's Mars 2020 Perseverance rover. Over 50 ATA engineers participated in mechanical engineering test and analysis services for its subsystems and components. Now I'll dive into the topic of our presentation. The Navy requires improvements in methods for reducing downtime and needs to improve the reliability of rotorcraft as they look to extend the life of their vehicles. Fatigue is a big consideration. In order to improve overall confidence in fatigue life predictions, we need to develop better testing strategies. Obviously, you cannot perform a fatigue test that represents the full service life of your helicopter because that would take over 20 years. Instead, the Navy is looking to develop compressed fatigue spectra so that they can perform accelerated testing that produces representative failure modes in a much shorter amount of time. By doing that, the U.S. government can perform more representative tests that will build our confidence in our designs for long-term mission success. The goal is to achieve at least 50% compression so that we can perform the tests at least twice as fast as we currently can. Overall, our intent is to develop a systematic approach to improving fatigue life predictions that eliminates the use of arbitrary criteria, enabling PM8A299 and others to improve their current accelerated fatigue testing capabilities. The operational need is for an accelerated fatigue test strategy that accurately reproduces the meaningful loading conditions that an aircraft experiences during its service life, but in a concise manner. The current strategy for conducting large-scale fatigue tests relies on the use of quasi-static loading, where loads are applied at relatively low frequencies to avoid exciting the mode of the structure and to enable precise control over the specific stress-strain responses. The biggest limitation of this approach, however, is that it takes a very long time to apply millions of fatigue cycles at low frequencies, thus the need for generating compressed spectra, or signals, to accelerate testing. Traditional methods for compressing or editing the signals have several limitations, including the inability to address multi-axial loading situations or material memory effects. Also, these methods require analysts who are very experienced in fatigue behavior who can make well-educated decisions on how to edit the signal. There is no standardized way of doing this, and the editing approach may differ from one analyst to another or from one signal to another. Extensive coupon testing may be needed to verify the signal editing approach for a signal that exhibits different loading characteristics. Finally, traditional signal editing methods are often limited to uniaxial quasi-static loading, where a single stress time history is used, and the compressed signals must be applied at very low frequencies that are not representative of the field environment. Alternatively, the use of wavelet transform allows us to characterize the time, frequency, and magnitude relationships of the loading signal, which we can preserve through the signal compression process so that the compressed signals are producing representative loading. The wavelet approach really allows the analyst to dig into the characteristics of the signal, identify which characteristics are important in terms of fatigue, and then preserve those characteristics during the signal compression process. The algorithm is driven by physical constraints to provide a systematic method for compressing the test signals without removing any key signal characteristics or relying on heuristics. This approach, therefore, produces optimally compressed signals within the given set of constraints that produce fleet representative failure modes. ATA's solution offers advantages over existing approaches by using the wavelet transform to preserve the time, frequency, magnitude relationships of the original signal so that the compressed signals can produce representative failure modes during testing. Because we preserve frequency characteristics, we can compress both input load signals as well as output stress-strain signals. In essence, our method enables dynamic testing. The algorithm incorporates physical constraints, so the user does not have to define arbitrary thresholds. With our method, we characterize the accumulation of fatigue damage and plastic strain in the original signal, and then continuously ensure that the compressed signal produces similar accumulation trends throughout the compression process. The algorithm is designed such that there is very little user input beyond the definition of the fatigue model. So given two users with the same fatigue model, they should get the same results. The results are also deterministic, so if you run the code twice, you will get the same answer. Ultimately, the compressed signals should representatively exercise the structure. With our method, we can do this using signals with durations that are a fraction of the original signal durations, which allows us to significantly reduce both test schedule and cost, while still producing field representative failures in a predictable manner. This slide describes in technical terms how ATA's systematic tool for compressing fatigue test signals works. The wavelet transform mathematically describes a signal's magnitude and phase as a function of time and frequency, which allows us to identify key signal characteristics. We then relate the time-frequency representation of the signal to a fatigue model so that we can identify the important characteristics in terms of fatigue and subsequently shorten the duration of the signal while preserving those characteristics. This is similar to what's done in audio engineering. A great example is a Super Bowl commercial. Let's imagine that you have a recording that's 35 seconds long that needs to be squeezed into a 30-second time slot. You could just play it a little faster, but it might sound like the classic cartoon chipmunks. So instead, you could apply the wavelet transform and shorten the duration while making sure that frequencies remain the same to eliminate the chipmunk effect. Of course, this may alter important phase relationships within the signal, so you would then need to reconstruct or realign the signal's phasing to ensure that the various frequencies interact correctly. Our damage squeezing technology essentially does the equivalent process. But instead of being concerned with audio quality, we're concerned with fatigue quality. We identify the fatigue characteristics using the wavelet transform and our fatigue model, shorten the duration of the signal, and then calculate the necessary changes in signal magnitudes to preserve those fatigue characteristics. And similar to the audio engineering example, we also need to reconstruct the phase relationships before we can recover a meaningful compressed signal. We then verify that the compressed signals have not altered the accumulation of plastic strain or fatigue damage and ensure that the higher signal magnitudes do not violate physical constraints. For example, we need to verify that our test actuators, or hardware that applies loads to the structure, is physically capable of applying these loads. Our algorithm can also be used in conjunction with a modal solution from a finite element model to account for input-output relationships. This model-in-loop behavior allows us to calculate the structure's response due to changes in input, which enables us to compress one or more input signals and enables dynamic testing. In partnership with our research institution, the Adaptive Intelligent Materials and Systems Center at Arizona State University, we have successfully completed both coupon-level uniaxial and biaxial testing. For uniaxial loading, we achieved 60% signal compression for a variable amplitude signal with local plasticity effects, and 94% compression for a similar signal without plasticity effects. These are great results considering that the level of signal compression directly corresponds to the amount of time savings. For example, an original uncompressed signal that would take 100 hours to produce a failure would only take 40 hours with 60% compression, and only 6 hours with 94% compression. In our case, our nominally 8-hour tests were reduced to just 3.3 hours and 30 minutes, respectively. Additionally, all results agreed with our analytic predictions. We very recently finished biaxial testing using both proportional and non-proportional loading conditions. Proportional loading is relatively straightforward, but non-proportional loading requires more fatigue considerations since there are complicated stress states that change over time. The latter is therefore much more challenging to predict. Our testing results for both types of loading produced favorable results, with similar levels of compression as the uniaxial testing and predictable results, including the preservation of cracking behavior for non-proportional loading. Given these results, we think that our technology readiness level is near a level of 5, and we are on track to achieving TRL 6 by the end of this year, with the completion of bending torsion and dynamic coupon testing. In this slide, we summarize the key features, advantages, and benefits of ATA's damage squeezing technology. In short, the technology allows for faster fatigue testing without sacrificing accuracy or reliability. The first feature, as previously described, is that the signal compression is performed in the timescale domain using the wavelet transform. This allows fatigue-critical time and frequency relationships to be identified and preserved, resulting in the compression signals exercising the structure in a very similar manner as the full-length signals. The second feature is that the signal's input-output relationships can be accounted for using a modal transient solver. This means that either the input, load, or the output, stress-strain, signals can be compressed, so the methodology can be broadly applied to both quasi-static and dynamic structures, thus enabling dynamic accelerated testing. Finally, the compression process is governed by physical constraints, which result in an easy-to-use systematic software tool. The benefit is that different users will get consistent field representative results in a predictably reduced amount of time. Overall, ATA's damage squeezing technology has the potential to cut months or even years off of an airframe fatigue test program. The transition of the damage squeezing technology to the Navy requires continued development and validation in order to create the most robust methodology possible. Our current Phase 2 contract essentially ends at the end of this calendar year, at which time ATA will make the advanced prototype available to the Navy. Our prototype is closely integrated with ATA's commercial IMAT software. IMAT, which stands for Interface Between MATLAB, Analysis, and Test, is an inexpensive suite of utilities offered by ATA which facilitates data sharing between MATLAB, analysis tools, and test software. The IMAT toolbox provides a framework for easily importing FEA simulation data and measured test data into the MATLAB environment to access its versatile programming and mathematical strengths. The advanced software prototype will have a graphical user interface to streamline the setup process so that the engineer performing the signal compression does not require advanced experience with fatigue. In addition, ATA has many fully trained personnel that are capable of helping the Navy and original equipment manufacturers with their challenging engineering needs. We are largely a services company and have a multi-pronged approach to commercializing technologies like this, where we will make this tool available with our IMAT software, but also provide the engineering service support should someone want us to perform the compression for them. The added value is that ATA can be involved in the full design, analysis, test process. Noting the Phase 2 experimental validation program has been very successful, it remained at the coupon level, so we are actively seeking a component-level test opportunity to further advance the technical readiness level for this technology. Regarding the commercial market opportunities, fatigue is a critical concern for a very broad range of defense and aerospace systems and other markets. From an aircraft perspective, all branches are looking to extend their vehicle service lives, and understanding fatigue is key to the safety around these decisions. Prime contractors are developing brand new rotorcraft platforms, which we all know are plagued by fatigue issues due to the relatively severe dynamic environments that they experience. Overall, our approach is not limited to a specific platform or even one industry. It is applicable to anything that has fatigue concerns, including reusable launch vehicles, new automotive platforms, and even amusement park rides. So ATA's technology has a very broad potential market use. Incidentally, these are all markets that our engineering services business already supports. ATA's damage squeezing technology offers optimally compressed fatigue test signals to achieve field representative failures in a fraction of the time of a conventional test. ATA expects the technology to transition well since we anticipate a robust user group will develop relatively quickly. It has immediate usefulness in the current Navy rotorcraft workflow and can be used in different program offices by prime contractors. We also anticipate licensing the algorithm to existing fatigue analysis software vendors so they can integrate it directly into their tools. ATA anticipates commercializing the technology in multiple ways. We have already discussed its integration into our IMAT software. ATA is more of a consulting company than a software development firm, so using the software to assist our customers is a natural extension to what we already do and how we operate. Likewise, when we perform methods development for our customers, we give away the technology, methods, and algorithms. This may sound like an unusual business model, but we have found that in doing so, not only do we delight our customers, but they typically return to us with harder and more challenging problems. This is why we're not trying to corner a small market with our software, but rather we're planning to include it with IMAT and will seek to help others to use it. In that vein, we anticipate providing training courses, whether virtual or in person, during non-COVID times. So ATA can help with signal compression either directly through hands-on computations or indirectly by ensuring the analysts performing the work have the tools they need to complete the job. Finally, one of the things that ATA does really well is end-user software support for various commercial software tools. We see an analogous opportunity with the damage squeezing technology to offer our customers excellent support. We welcome you to visit Tyler and me in our virtual booth here at the Department of Navy Forum for SBIR STTR Transition, or please feel free to reach out by email or phone if you'd like to learn more about our damage squeezing technology or ATA's general structural and mechanical engineering capabilities. Thank you so much for your interest in ATA and our accelerated fatigue testing project.